Next topic is quadratic programming. It is also non-linear programming problem. Quadratic programming is also non-linear programming problem. And quadratic forms in matrices. Okay, I think this semester, second semester, you are having matrices chapter, quadratic forms, X transpose AX is a quadratic form. X transpose AX is the quadratic form. Such type of quadratic form will be the objective function in this non-linear programming problem. So this is quadratic programming. Quadratic programming. And if in NLPP, the objective function contains quadratic form. Objective function contains quadratic form. What is the model of quadratic form? X transpose dx or ax. Okay, whatever it is. X transpose ax. Then it is called quadratic programming problem with the constraints types are non-linear. Linear type constraints. With constraints, linear type constraints. Quadratic form X transpose ax. Then NLPP is called quadratic programming problem is called QPP. I will write QPP. In general, in quadratic programming, the objective function is non-linear. Objective function is non-linear and constraints must be linear. This is very important, all of you. Constraints must be linear. Constraint must be linear constraints. And what is the general form of quadratic programming problem? General form of quadratic programming problem is optimize. Here you go. Optimize means maximize or minimize. Z equal to, see the objective function, all of you, this is very important. Summation Cj into Xj. N variables are there. So j equal to 110 means what? C1 x1 plus C2 x2 Cn xn. That means linear function here. And coming to here, this is 1 over 2. Okay, space is not suitable here. Let me write once again. Optimize means maximize or minimize. Z equal to summation j equal to 1 to n Cj into Xj means C1 x1 plus C2 x2 up to Cn xn plus 1 by 2 into double summation. K equal to 1 to n, j equal to 1 to n. Both are to write the quadratic expression. Xj into some element djk. Like in A, what are the elements? You can write A also, small a also, but I am mentioning D, xk. Okay, this is the objective function. 1 by 2 into double summation xj dj means what? This is the structure of this one is, see, I'm giving here. The structure of this one is like some x1 x2 quadratic expressions, or x1 square plus x2 square plus x3 square plus some 2x1 x2 2x1 x3, like this. That means definitely the terms must be square. The degree must be, degree of every term must be 2. That is called quadratic form. That is why here 1, here 1, that is 2. This is objective function. subject to the constraints. Subject to the constraints. What are the constraints types? I told you linear type constraints. So as usual, in simplex method, these are the constraints. This is j equal to 1 to n, and how many constraints I'm taking? I equal to 1 to m, and xj greater than or equal to 0 for all I comma j. Xj greater than or equal to 0 for all I comma j, and j is enough for all j. This is the structure of quadratic programming problem. Okay, once again, the objective function is what? One linear function and plus one quadratic function, and the subject to constraints types of what? Linear type constraints, and non-negative restrictions. In matrix form, the quadratic programming problem may be written as optimize z equal to linear function means what? I can write cx matrix form, summation 1 by 2 is there, summation, there is no summation in matrix form, directly 1 by 2. Okay, what is that? Xj into djk into xk. That can be written as, quadratic form, matrix form notation, x transpose dx, subject to the constraints ax less than or equal to b, and x greater than or equal to 0. Okay, this is the matrix. Capital X means, already I told you it is a solution vector. So it is a column vector always. When this is column vector, this is C. C is called cost matrix. C1, C2, and so on, Cn. It is a row matrix for the product, Cx. Then if I take C into X, then I will get C1x1 plus C2x2 and so on. And this matrix B, right side matrix, this is also column matrix. This B matrix, B1, B2, Bm, whole transpose. And capital D matrix. What is the capital D matrix? I told you djk. This is n by n matrix. Done. And what is the matrix A? A is there. Capital A is the matrix. These are the elements A, I, J. And what is the order of the matrix? M by n matrix. Okay. And the conditions are same. If the objective function in quadratic programming problem is of minimization, that means objective function is minimization, then in the quadratic form x transpose dx, the matrix D is symmetric matrix. Already you know this one. In the matrices, in a quadratic form, what is the matrix D? Definitely it must be a real symmetric matrix. Okay, then only we can apply the orthogonal transformation to transform it to diagonalization, right? Matrix D is symmetric, and this is important, and positive definite. I told you, when positive definite means what? Last class, objective function is convex. Therefore objective function is convex. Positive definite means objective function is convex. Hence, it possesses, convex function possesses definitely minimization. Next, if the objective function in quadratic programming problem is of maximization, then the matrix D, then D is symmetric. Definitely it must be symmetric. D is symmetric and a negative definite. Therefore, negative definite means what? Therefore, objective function is concave. Concave means what? It possesses maximization. Concave means what? It possesses maximization. Now the next one is, this is introduction of the quadratic programming. Now how to solve it? Okay, we solve to solve this one, Kuhn-Tucker conditions. Kuhn-Tucker conditions for quadratic programming problem. Kuhn-Tucker conditions for quadratic programming problem. Now I have to write the Kuhn-Tucker conditions. The necessary and sufficient KT conditions. The necessary and sufficient KT conditions to get an optimal solution. Optimal solution means maximum or minimum. Optimal solution to the maximization problem. To the maximization quadratic programming problem, subject to linear constraints. Subject to linear constraints are derived as follows. So derivation is not important for you, but theory is very important. Step 1. Stepwise I'm giving. Okay. In many of the textbooks, steps will not be given. So I'm giving stepwise to understand the concept clearly. First, step 1, introduce slack variables. Introduce slack variables, SI square and RJ square to the constraints. Then QPP, quadratic programming problem becomes. Now, what is the objective function? I am considering maximization of function of f of x z, or you can write, what is this? Cj into xj, j equal to 1 to n minus 1 by 2 double summation. What is this? J equal to 1 to n, k equal to 1 to n, xj into djk into xk. Done. This is objective function. And subject to the constraints, all of you, this is very important. What are the constraints? Aij into xj. Actually, what is this? Less than or equal to bi. J equals to 1 to n. To convert less than or equal type constraint to equality type constraint, we are adding squared slack variable as in Kuhn-Tucker condition. So in place of, to convert this less than or equal to type, what I have to add? Squared slack variables, that is plus si square equal to what? Bi. I equal to 1 to m constraints are there. And one more important point is what here in quadratic programming problem, what we are doing, these conditions are there now, these non-negative restrictions. These non-negative restrictions are also included in the constraints. In general, in simplex method or whatever the previous Lagrange's method, Kuhn-Tucker conditions, we are not involving these non-negative restrictions into the problem. Now in quadratic programming problem, these non-negative restrictions are also included. How those are included, I'm giving here. See, first, this is rough work here. Xj greater than or equal to 0. Convert this to less than or equal to 0. Xj less than or equal to 0. Now, convert this less than or equal to equal to by adding rj square. Rj square are the slacks, another slacks. So, what is this point? Minus xj plus rj square equal to what? 0. How many constraints? These are n constraints are there. This is idea. Okay, now this is the problem. Step 1 problem is what? In the given constraints as well as non-negative restrictions, we are converting them to equality type constraints. Okay, any doubts? In this step 1? Step 2. Now, forming Lagrange's. Now, all are equality type constraint, therefore forming a Lagrange's function now. The base of Kuhn-Tucker condition or nonlinear programming, whatever it is, the base is Lagrange function. Okay. Forming the Lagrange's function as, how to form Lagrange's function? L. How many variables? X. Capital X means n variables are there. Slack variables, yes. Another slack variables are Lagrange's multipliers lambda and another Lagrange multiplier mu. What is mu? Let us see. What is mu? Let us see. What is this? Is Lagrange's function objective function minus summation lambda I into the given constraints. What are the constraints here? A ij xj plus si square minus bi. This is I equal to 1 to m. This is one constraint. That means this part is over. This part is over. Now, what are the another constraints? Minus xj. For those constraints, I am taking mu j or the Lagrange's multipliers. J equal to 1 to n mu j. This is for what constraints? Non-negative restrictions. Rj square or j square. This is Lagrange's function. Here lambda I comma mu j are Lagrange multipliers. Okay, right? Now, what are the necessary conditions? Step 3. Same procedure is same, but we are applying for quadratic programming problem and we have to simplify those conditions, right? Now, the differentiate L Lagrange's function partially with respect to, these are the necessary conditions I'm giving here, partially with respect to the components, with respect to the unknowns. What are the unknowns? X, S is unknown, R is unknown, lambda is unknown, mu is unknown. With respect to unknown, then we have, now this part is very important. We have first one. What is this one? See, dou L by dou xj equal to 0, j equal to 1 to n. Done? Okay. Now, what is this one? What is this? Is nothing but L. L means what? This one. So, dou f by dou xj, and coming to this part, right? With respect to xj, this term is also there, right? First, better, all of you, let me write L elaborately by substituting f of x also. Then it will be very clear for you. L is equal to, what is f of x? What is f of x? Summation cj into xj, j equal to 1 to n, okay, plus minus 1 by 2 into, okay, it's very small, 1 by 2 into double summation xj djk xk, j equal to 1 to n, k equal to 1 to n. This is objective function, minus summation j equal to 1 to n lambda I into, what are the constraints? Aij into xj plus si square minus bi. This is over. And another one is what? J equal to 1 to n mu j into minus xj plus rj square. This is completely L function by substituting f of x. Now, first condition, dou L by dou xj equal to 0, j equal to 1 to n. What it gives? Next line I'm writing, gives, first, what is this value? With respect to xj. With respect to xj means what is its quotient? Cj. Just write cj minus 1 by 2 minus 1 by 2 will not be there. Why? Because this is what? Square. This is what? In terms of square, quadratic form. So 2 into something will be there. That 2, this 1 by 2 gets cancelled. Okay. So this becomes what? summation. With respect to xj we are doing, so k will be as it is, k equal to 1 to n. xk, what is the xj quotient? xk into djk. djk minus this part is over. Coming to here, this part, summation I equal to 1 to m lambda I into aij. Lambda I into aij. This is over with respect to xj, right? Next one, this is last step, plus xj derivative minus 1, so you will get mu j equal to 0. j equal to 1 to n. j equal to 1 to n. This is the first condition. So I'm underlining this. This is the first condition. Coming to second condition. What is that? Dou L by dou Si equal to 0. Dou L by dou Si equal to 0. What is this becomes? Si means where Si? Here. So what you will get? 2 Si will be derivative. 2 Si into lambda I will be the derivative. Right? So that gives what? 2 lambda I, 2, what it gives after derivative? Just wait. With respect to yes now? With respect to yes means, yeah, only that part will be there. So 2 lambda I into Si will be 0 minus I equal to 1 to m. I equal to 1 to m. Okay. And I told you already this condition gives what? Gives, this condition gives lambda I into constraint gix. Already you know that part. So in Kuhn-Tucker conditions, what are the constraint here? aij into xj minus bi. This is j equal to 1 to n. This part is equal to 0. Already by simplifying this condition, we are getting this in Kuhn-Tucker condition. Last class, you can listen that class once again. This is the second condition. Done? Right. Coming to third part. Third part is what? Dou L by dou mu j equal to 0. Dou L by mu j equal to 0. What this gives? Mu j means what? Here. So what? Dou L by dou rj. Sorry. Another unknown is not mu j, rj. Dou L by dou rj 0 means what? You will get minus 2 mu j rj equal to 0 you will get. J equal to 1 to n. J equal to 1 to n gives, and if I simplify this, okay, if I simplify this, you will get mu j into xj. Constraint is what here? Constraint is what? Xj. So mu j multiplied by here lambda I. What is the constraint? Corresponding to lambda I, what is the constraint? This was the constraint. So multiplication 0. Corresponding to rj, what is the constraint? Xj. So mu j into xj 0, j equal to 1 to n. J equal to 1 to n. Okay, this is another constraint. And the fourth one is, and the fourth condition is the given constraints, like same Kuhn-Tucker conditions. There is no change, but extra is this mu j, xj less than or equal to bi, j equal to 1 to n, j equal to 1 to n, j equal to 1 to n. This is I equal to 1 to m. This is I equal to 1 to m. These are the constraints. This is another one, right? And the fifth KT condition becomes fifth one. What is this fifth one? The given constraint minus xj. Directly you can write. No need of that one. Constraints, all non-negative restrictions are also involved. So these are taken account into Kuhn-Tucker conditions. The non-negative restrictions also taken care. Okay, xj greater than or equal to 0, and this is another condition. And the last one, sixth KT condition for quadratic programming problem, all these are xj, sj and rj, all must be greater than or equal to 0. This is the last one. There must be no negative value for this lambda, mu, x and slack variables si and rj. Okay, these are the 6 Kuhn-Tucker conditions for the quadratic programming problem. Okay. Now this is important. In the above conditions, in the above conditions, there are two conditions are there. Lambda I into Si equal to 0 and mu j into xj equal to 0. These two conditions are there. Okay, mu j into xj, one condition, and lambda I into Si, this is condition. These two conditions are called complementary slackness conditions. Complementary slackness conditions. Complementary slackness conditions. That is, what is meaning of this one? That is, for lambda I into Si equal to 0, lambda I into Si equal to 0, lambda I into Si equal, what is the meaning of this lambda I into Si equal to 0? First one, lambda into Si equal to 0. What I'm giving this meaning of this, in solving QPP, lambda I and Si cannot be basic variables, at a time. That means in simplex table, lambda I, Si both cannot be basic variables. Definitely one of them must be non-basic. Both cannot be basic variables. That is, still if any doubt I'm giving, that is when one of them is basic variable, the other must be non-basic variable. Non-basic variable. Then this is the condition complementary. Similarly, for mu I into xj equal to 0, both mu j and xj cannot be basic variables at a time. Cannot be basic variables at a time. These are the complementary conditions. In solving, this is important, in solving QPP, the complementary slackness conditions must be taken care. This is important point. Okay. Now, to solve QPP, the original method is to solve Kuhn-Tucker conditions are over now. To solve QPP, we have Wolfe method, Wolfe's modified simplex method, simply called Wolfe's method. Simply called, it is called Wolfe's method. Now, let us see what is the method. If any doubts in this theory, you can raise the questions. Wolfe's method. And remember, you have to remember the steps definitely in solving quadratic programming problem. Step 1. Step 1 is introduce artificial variables. Aj, j equal to 1 to n. Introduce artificial variables aj, j equal to 1 to n in the first Kuhn-Tucker conditions. In the Kuhn-Tucker conditions 1. In the Kuhn-Tucker conditions 1. What the Kuhn-Tucker conditions 1 say? When I mention this 1 means what? Here, there is a 1 here. First count, yeah. In this one, this underlined one. In this Kuhn-Tucker conditions, I have to add artificial variables. Okay, that is why I'm giving the step by step the method 1. That is what Cj minus, what is that part with respect to, we did j now, so this must be k equal to 1 to n xk djk minus summation lambda I into aij plus mu j. Up to here, the first kt condition. Up to here, the first kt condition. I have to add what? Artificial variable. I have to add what? Artificial variable. Done. This is over. This can be taken as now what one can write. You can multiply this by minus also, doesn't matter, right? Okay. So why I'm adding artificial variable, that will give clarification for you. So this value is, take every, no, it doesn't matter. This is the first condition, no problem. Add artificial variable in the first Kuhn-Tucker conditions. Step 2. Step 2.
Setup box
సెటప్ బాక్స్ అక్కడ ఇంటర్నెట్ది అక్కడ. Step 2, apply phase 1. You know, two-phase method. Apply phase 1 of the simplex method. Phase 1 of the simplex method to check the feasibility of the constraints. To check the feasibility of the constraints, or the constraints ax less than or equal to b, of the constraints ax less than or equal to b. Okay, now to obtain how to write this, you write like this: to obtain desired feasible solution, solve the following problem. What is the problem? So now I'm formulating the problem. Minimize z equal to summation aj. Already we have added artificial variables in the objective function. First constraint, subject to what are the constraints here. The first constraint is our first kt condition, xk djk k equal to 1 to n plus summation lambda I into, I'm writing the first condition, Kuhn-Tucker condition, minus mu j plus aj equal to minus cj. This is the first Kuhn-Tucker condition. That is the first constraint in this linear programming problem. And one more point here, I'm taking multiplication by minus. Yeah, I'm taking take this cj that side. Okay, this constraint and our first constraint is same. What is the part here? Everything here, take this cj onto that side, or everything onto this side. What I am telling you, this I will write shortly here. This is how to, here plus aj we are considering, and we are taking minus cj onto right side, so there must be a confusion here. So I will write this constraint as take this cj that side multiplied by minus sigma xk djk plus summation lambda I aij minus mu j will be there, and plus aj equal to, actually this aj I have to add aj like this, minus cj, like this. Okay, the concept is like this. And in problem it will be very clear for you. After multiplying by minus, remember, after multiplying by minus, taking cj that side and add artificial variable. That is very important. Next, what is the next constraint? The given constraints are what? Equality type constraints. After adding slack variables, si square equal to bi. This is I equal to 1 to m. I equal to 1 to m. This is j equal to 1 to n. Okay, this is also j equal to 1 to n. Now, what are these two are the constraints. That's it. And what are the remaining constraints? Are all the constraints lambda I, mu j, next one si, next one what? You write capital AJ. Done. And any other constraints, all are greater than or equal 0 for all I comma j. And complementary slackness conditions you have to write. That is very important. Lambda I into si equal to 0 and mu j into xj equal to 0. These are complementary slackness conditions. These conditions must be satisfied in each simplex table. Complementary slackness conditions. Okay, now this is my entire problem. This is my entire linear programming problem, phase 1 problem, particularly phase 1 problem. Okay, now solve the phase 1 problem to get the feasible solution. You know what I mean by feasible solution, which satisfies all the constraints. To get the feasible solution. Done. Now step 3. Apply phase 2. Apply phase 2 of the simplex method. Phase 2 of the simplex method to get an optimal solution. That's it. Okay, this is completely a Wolfe method to solve quadratic programming problem. Now I'm going to solve the problem. Okay, listen, understand the problem carefully. It's very easy one actually. If you thorough with the scheme, the problem is very easy. Use Wolfe method to solve quadratic programming problem. What is the problem? Maximization of z is equal to 4x1 plus 6x2 minus 2x1 square. This is also minus 2x1 x2 minus 2x2 square, subject to the constraint x1 plus 2x2 less than or equal to 2, x1 plus x2 less than or equal to 2, and x1 x2 greater than or equal to 0, and x1 x2 greater than or equal to 0. Solution. Just give me 2 minutes time. Okay. Now, first, I have to write the conditions, KT conditions first. Okay. Objective function is what I'm writing here. Objective function f of x1 x2 is what? 4x1 plus 6x2 minus 2x1 square, 2x1 x2 minus 2x2 square. So this is the quadratic structure, and this is linear structure. Cx is here and x transpose dx is here. Okay, right? Next, the necessary KT conditions. First, you have to write this one. Okay, like a previous method. The Kuhn-Tucker conditions for the given quadratic programming problem are one by one. Okay, before that, let me add slack variables now. Okay, the QPP can be written as maxima z equal to 4x1 plus 6x2 minus 2x1 square minus 2x1 x2 minus 2x2 square, subject to I have to convert the constraints to equality type now. So x1 plus 2x2, what this one, slack variable, squared slack variable. And coming to these constraints also, so minus x1 plus what I have added, rj square. So this is r1 square. Convert first to less than or equal to type. X1 greater than or equal to 0. So minus x1 less than or equal to 0. Similarly, minus x2 less than or equal to 0. So another one is what? Minus x2 plus r2 square less than or equal to 0. And what are the variables? All the variables s1, s2, r1, r2, all are greater than or equal to 0. Okay. Next one is, what is this? After writing this one, I have to construct Lagrange's function. The Lagrange's function is capital L. L of what? How many variables? x1, x2. How many constraints are there? Only one constraint, lambda 1. And remaining to non-negative variables, there are two constraints are there. So two another Lagrange's multipliers, right? Done. And r1, r2 is equal to first objective function. What is objective function? I have to write 4x1 plus 6x2 minus 2x1 square minus 2x1 x2 minus 2x2 square. This is objective minus lambda 1 into the constraint. What is the constraint? x1 plus 2x2 plus s1 square. This is over. Then minus 2 left side. Next, another one, the given non-negative restriction. So r1 square. Here s1 will be there. S1 also there. Minus mu2 into minus x2 plus r2 square. Minus s2 plus r2 square. Lagrange's function is over. Now the necessary conditions. For maximization are, what is the first one? Dou L by dou x1 equal to 0. Okay, I'm simplifying directly now. Dou L by dou x1 equal to 0 means what? This is 4 will be here. Minus 4x1 is here. Minus 2x2 is here. Next one, here x1 is there. So minus lambda 1. And next plus mu1 equal to 0. Next one is dou L by dou x2 equal to 0. Dou L by dou x2 means 6 minus 2x2 minus 4x2. Then next one, x2 means minus 2 lambda 1 plus mu2 will be there. Okay, this is also over. Next one is what? Dou L by dou lambda 1 equal to 0. Dou L by dou lambda 1 equal to 0. So lambda 1 derivative 1. So remaining part becomes what? I will get this one completely. S1 square minus 2 equal to 0. Minus is negligible anyway. Next one is what? Dou L by dou mu1 equal to 0. That means I am getting minus x1 plus r1 square directly. Next one is what? Dou L by dou mu2 equal to 0. That gives what? Minus x2 plus r2 square equal to 0. Next one is what? With respect to r1, dou L by dou r1 equal to 0. That is minus 2 mu1 r1 equal to 0. Minus is there? Yeah, minus 2 or minus. You can neglect minus also, doesn't matter. Dou L by dou r2 equal to 0. That is minus 2 mu2 r2 equal to 0. So s will not be there. Already s is included in lambdas, so s will not be there. Now these are the conditions over. After simplifying, now I am writing, after simplifying all these conditions, we get we get. Now first two equations as it is, and take the constant that side. So what is the first one? 4x1 plus 2x2 plus lambda 1 minus mu 1 equal to 4, first one. Next one is what? 2x1 plus 4x2, yeah, I'm taking minus common, plus 2 lambda 1 minus mu 2 equal to 6. Okay, next second conditions, constraint part, x1 plus 2x2 plus s1 square equal to 2. Third part, third condition, complementary slackness. See why I'm writing only these after simplifying all of you. Remember what are the necessary conditions. This is my problem. I am considering only first KT condition and the second KT condition, Kuhn-Tucker conditions. That's all. Remaining are complementary slackness. So I'm writing those directly. Third conditions are what? Complementary slackness conditions. SI is included here. Mu j into xj equal to 0. These are complementary slackness conditions. Complementary slackness. If any doubt in this complementary slackness condition, that will be clear in solving the problems. Okay, and these are the conditions. And last one is what? All the variables, x1, x2, lambda 1, mu 1, mu 2, s1, all are greater than or equal to 0. All are greater than or equal to 0. Now I have written this one. Okay, now what I have to do? These are the KT conditions now. Okay, these are the KT conditions. After simplifying this, we get the KT conditions as and I have to apply two-phase method. Remember, in the first KT condition only we are adding artificial variable. Why artificial variable? Since there is no basic variable here. By adding one artificial here and here. Okay, so the thing now, the problem introduce how many artificial variables? Since there are two constraints, two conditions in one, two equations in condition 1, I need two artificial variables. Introduce the artificial variables. Introduce the artificial variables a1 and a2. A1 and a2 in the first two equations. In the first two equations of 1. Then the modified LP problem. That is why it is called Wolfe modified method. The modified linear programming problem becomes now. Modified linear programming problem becomes now. See the problem. What is objective function? Already I told you, minimize. Objective function is minimize z equal to, two constraints will be there, two artificial variables subject to, see how to write. In the first one, a1 plus a1 here, next plus a2 here. So I'm writing those two first. Subject to 4x1 plus 2x2 plus lambda 1 minus mu 1 is equal to 4. Next, what is the next constraint? 2x1 plus 4x2 plus 2 lambda 1, right, minus mu 2 is here. I'm leaving some space here. Why? Because it belongs to mu 1 column. So minus mu 2 equal to how much? 6. And plus a1 is here, and leave some space in the second constraint. Plus a2 is here. Then a2. And what is the next constraint? Given constraint. Okay, I will write one in the same column only. x1 plus 2x2 plus s1 square. So I'm writing plus s1 square equal to how much? 2. And all the variables x1, x2, lambda 1, mu 1, mu 2, s1 is not there now, right? Okay, s1 is not there. That is why I have not included this next one. A1, a2, mu 1, mu 2, all are s1 is here. S1, all are greater than or equal to 0. all are greater than, and s1 square is there. So no need of this s1 greater than or equal 0. Square means always non-negative. So these are greater than or equal to 0. Is the phase 1 problem. Is the phase 1 problem. You know how to solve phase 1. What is the first thing? Convert this minimization to maximization. Then objective function becomes what? Maximize. Just I'm giving here. This is maximize j star equal to minus a1 minus a2. Minus a1 minus a2. That is objective function and subject to these constraints. Subject to these constraints. Right? Okay. Now, solving phase 1. I think you know how to solve this problem. Now I'm giving the table, simplex table. First, cost vector of the basic variables. Next, column is for basic variables. Next, basic solution. Basic solution, that is known as xb. Okay. Next one is what? Write list all the variables. How many variables? x1, x2, lambda 1. Okay, let me see this table. Lambda 1, next mu1, mu2, mu1, mu2, next a1. Okay, s1 I will write. S1 done. Next a1, next a2, a1, a2. So I have to list the, these are the separate columns. And close here, right? And what are the initial basic variables? Starting initial basic variables, see a1, starting initial basic variables are a1, a2 and s1 square. S1, nothing but s1. So it is having column 1 0 0, a2 is having column 0 1 0, s1 is having column 0 0 1, s1 is having column 0 0 1. Okay. Now, so what are the starting basic variables? a1, a2, s1. And what is the cost of a1 after transforming to maximization function? I have given here maximization of minus a1 minus a2. So cost of the artificial variable becomes minus and the cost of slack variable always 0, right? And what is the basic solution at the starting stage? The right side vector 4 6 2. So I'm writing 4 6 2. And what is the x1 column? 4. Okay, whenever I will write this one, see all of you, I'm giving short techniques for you. Basic solution from this one words, you write this. Now, whenever a1 is the first basic variable, it possesses the column 1 0 0 and net evaluation. These are called net evaluations 0. a2 is the second basic variable having second identity column 0. S1 is the third basic variable having the third identity column 0 0 1 0. Now x1 column from the given system 4 2, see x1 column is here 4 2 1. Okay, now write that one 4 2 1. X2 column is what? Similarly 2 4, that is 2. And lambda 1 column is what? Lambda 1 1 2 0. Lambda 1 column 1 2 0. And what is mu1 column? Minus 1 0 0. Mu2 column 0 minus 1 0. Right? All are over. Now what are the net? This value is objective function value. This value is objective function value z equal to cb into xb. That means this into this into this. Right? Okay. Now minus 4 minus 6. So this is minus 10. Minus 4 minus 6 minus 10. And what about this? And what is the cost of all the variables here? 0 except these two. Except these two. Minus 1 minus 1. So what is this? Minus 4 minus 2 minus 6. And here minus 2 minus 4 minus 6. Is it correct? Next one minus 1 minus 2 minus 3. This is plus 1 and this is plus 1. And which variable enters to improve the solution? Most negative. Most negative. And remember, here you have to keep in mind lambda 1 into s1 equal to 0, mu1 into x1 equal to 0. Done? And since s1 is the basic variable here, s1 is the basic variable here, right? And another one is what? Mu2 into x2 equal to 0. These are the complementary slackness conditions. These are the complementary slackness conditions. Means what? Whenever S1 is the basic variable, lambda 1 cannot be basic. Lambda 1 cannot be basic. Right? Anyway, in the most negative, where is this one? Most negative minus 6 here. So you can enter any one. I will enter x1. When entering x1 variable, keep in mind that mu1 cannot be basic. Is mu1 is basic variable? No. So I can enter. Right. Write that step here. Write that step here. What is that? Since mu1 is not basic variable, since mu1 is not basic variable, and x1 having most negative net evaluation, we can enter x1 as basic variable. We can enter x1 as basic variable. Done. This part is clear, right? Now when x1 is basic variable, using the minimum ratio principle, which one is leaving? Using the minimum ratio principle, 4 by 4 1, 6 by 2 3, okay, and a 2 by 1 2. So which is minimum? This is the minimum. So a1 is leaving. So a1 is leaving. Done. Now the next simplex table is what? Next table is again cb. I will write basic variable, basic solution xb, and write all the variables x1 x2 lambda 1 mu1 mu2 s1 a1 a2, and what are the cost of all the variables? Zeros except artificial variables. And done. Now what are the basic variables? In place of a1, x1 is entering, a2 is as it is, s1 is as it is. This is 0 and this is s1. Now x1 is the first basic variable having first identity column, a2 is the second basic variable having second identity column, s1 is the third basic variable having third identity column. Over. Next, what is the next calculation? Pivot row. This is called key element or pivot element. Divide every value by the key value. That means 4 by 4 1, 2 by 4, like that. Okay, so 1 by 1 I have to write. Okay, 4 by 4, just 4 by 4, this is 1. Next one, what is x2 column? 2 by 4, next 1 by 4, this is 2 by 4, next 1 by 4, next minus 1 by 4, next mu2, what is mu2? 0 is there, 0 by 4, next a1 value is what? 1, so 1 by 4, 1 by 4. Next one, what is a2 position? See, coming to this, okay, this position, shortcut technique, I think you might have known this. 6 4s are 24, 24 minus 8, this into this minus this into this. 6 4s are 24, 24 minus 8, 24 minus 8 16, 16 divided by 4, 4, this value 4. Next one, x2 position, x2 position means this one, 4 4s are 16, 16 minus 4 12, 12 by 4 3, this position is 3. Next position, what is this? Lambda 1 position. Table is not, yeah, now it is okay. Now this position, okay, this position, lambda 1 position, 2 8, 4 to the 8, 8 minus 2 8, this one, these two, okay, 8 minus 2 6, this is 6 by 4, correct? Right. Next one, mu1, this is 0 and plus 2 by 4. I'm not simplifying this, as it is 2 by 4 I'm writing. Mu2 value minus 4 0, minus 4 by 4 minus 1. Next in a1, this is 0 and this is 2, minus 2, so minus 2 by 4. Coming to this value, 2 4 is 8, 8 minus 4 4, 4 by 4, this is 1. Next one, coming to which value? X2 position, this value, 2 4 is 8, 8 minus 2 6, so this is 6 by 4. Done. This is 16. 16 minus 4, 12. 12 by 4 means 3. Yeah, okay, no problem. And coming to this lambda 1, this is 0 and minus 1 by 4. Mu 1, this is 0 and this is plus 1 by 4. Next mu 2, this is 0 and this is 0. So this is 0 and this is 0 and this is negative 1. So negative 1 by 4. Now this part is over, right? Now calculation again, net evaluations calculations. This is what CB into XB, this Z value. CB into XB means you will get minus 4 and 0, 0, you will get minus 3 here. Here minus 6 by 4 you will get. And here you will get minus 2 by 4 and you will get 1 here, here plus 2 by 4. Done. And which is most negative? Most negative means x2. So this is entering. Since x2 having most negative net evaluation, it enters the table. It enters the table as basic variable. Since, see, whenever x2 is entering, since mu2 is not basic variable, because this is complementary condition. Okay, since mu2 into x2 equal to 0, mu2 is not basic variable. Done. Okay, not basic variable. Now which one is leaving now? This 1 by 2 by 4, that is 4 by 2, 2, 4 by 3, this is 4 by 6. So which one is leaving now? This is the minimum. 4 by 6 is the minimum. Done. So this is the S1 is leaving. S1 is leaving variable. Now next table. And by minimum ratio principle, which one is leaving? S1 is leaving. S1 is leaving. Now next table, CB, basic variable, basic solution XB. Now all the variables x1, x2, lambda 1, mu1, mu2, s1, a1, a2, negative 1, negative 1. These are cost of the variable zeros. You applied same method now, simplex procedure, right? And what are the basic variables now? x1 as it is, a1 as it is. Now in place of s1, which one is entering? x2 is entering. So 0, negative 1, 0. x1 is the first basic variable, 1, 0, 0, net evaluation 0. a1 is the second basic, sorry, a2. a2 is the second basic variable. Next one, x2 is the third basic variable, third identity column. Done. Next, key row. Key row means divide this by key value, 1 by 6 by 4. This is 1 by 6 by 4 by 6 and minus 1 by 4 by 6 by 4 minus 1 by 6. Okay, I am writing the table values. Okay, you can calculate. This is what? 6 by 4. This is 4 by 6. Done. Next, this is minus 1 by 6. This is 1 by 6. This is 0. Wait. Yeah, this is 0. And this is 2 by 3. This is 2 by 3. And a1. What is a1? Minus 1 by 4. Minus 1 by 4 by 6 by 4. Minus 1 by 6. Actually, you can delete this a1 when it is leaving. No need to write. Okay. Next, these values are 4 by 6. And this becomes 2. And lambda 1 value 1 by 3. This is 2. This is negative 1 by 3. This is 0. This is 0 minus 1. and negative 1 by 3, negative 2. Okay, done. And a1, what is a1? This is 6. 6 plus 2, 8. 8 by 4 into 4, and 2 by 4, 2 by 6. This is 2 by 6. And a1 next position, this position, minus 12. Minus 12. Okay, anyway, no need to calculate this one. Okay, this is minus 12. Minus 12 by 16. And coming to this, if I 12 plus 12, 0. This value is 0. This value is 0. Now this value is negative 2, z value, and coming to this, negative 2. This is 0. This is positive. This is plus 2, and this is plus 1. Plus 1. So which one is most negative? Only one negative is there, lambda 1. Lambda 1. When lambda 1 entering into the basis means what? What is the condition? Mu j into lambda j. Is it correct? Mu j into lambda j. What are the complementary slackness conditions? Lambda 1 into s1. Okay, yeah. Only one complementary condition is there. Lambda 1 into s1 equal to 0. So when I am entering lambda 1, s1 cannot be basic. S1 cannot be basic, right? We can enter lambda 1 as basic variable. Lambda 1 as basic variable, as s1 is not basic. S1 is not basic variable. So complementary slackness condition satisfied here, right? And which one is leaving variable? I have to apply only positive elements. This is 2 by 3. That is 2. This is 1. So 1. A1 is leaving. A1 is leaving. Done. So last table. A1 is leaving using minimum ratio principle. Using minimum ratio principle. Next table. CB, basic variable, basic solution, x1, x2, lambda 1, mu1, mu2, s1, and you no need to write a1, a2, right? No need to write a1, a2, because once artificial variable leaves the table, they will not enter the simplex table again. They will not enter the simplex table again. So no need to write the columns of artificial variable. Now the basic variables are what? X1, lambda 1 is entering, x2. So 0, 0, 0, 0, 0, 0, 0, 0, 0. Now x1, 1, 0, lambda 1, 0, 1, 0, x2, 0, 0, 1, 0. Right? And as well, you calculate, you know the technique. This is 5 by 6. And a mu1 column minus 1 by 3, 0, 1 by 6. And a mu2 column 1 by 6, minus 1 by 2, minus 1 by 12. And this is 0, minus 1, 1 by 2. So this value, z value, now 0. Everything is 0. Okay. Since there is no artificial variable, there is no artificial variable in the optimal table of phase 1. This is optimal table, right? All are greater than or equal 0. In the optimal table of phase 1, it is feasible. Phase 1 is feasible. Phase 1 is feasible. Feasible means what? Possess solution. Hence go for phase 2. Hence go to phase 2. Hence go to phase 2. Right? If I apply phase 2, we are getting the solution directly. We are getting the solution directly. Right? What is phase 2 now? CB, basic variable, basic solution, x1, x2, lambda 1, mu1, mu2, s1. Same. You will get the solution. Actually, no need to write this phase 2 also. Directly from phase 1 problem, you can write the solution also. And what are the basic variables? x1, lambda 1, x2. What are the cost? Now you have to change the cost of the variables. You have to change the cost of the variables. What are the cost? Original cost of x1 in the given problem. In the given problem, what is the cost of x1? 4. This is 4. And no, not here. Where you can write. No need to solve phase 2. No need of this one. Why I should confuse you? No need of this phase 2. You can write directly from the phase 2. You can go to phase 2. You write, you can, even in examination also, you can write directly. When we solve phase 2, we have the solution. We have the solution. See, exactly. Here it is. x1 equal to 1 by 3, x2 equal to 5 by 6, and lambda 1 equal to 1. Okay, those are the basic variables. We have the solution. X1 equal to 1 by 3, x2 equal to 5 by 6, lambda 1 equal to 1, and the remaining are non-basic now. Remaining are non-basic solutions. So what are the remaining? Mu1 0, mu2 0, s1 0. Right? Done? Okay, hence what is the objective function? Maximize z equal to, what is the function actually? Original function 4x1 plus 6x2 minus 2x1 square minus 2x1 x2 minus 2x2 square minus 2x2 square. Substitute this x1 and x2 values. 4 into 1 by 3 plus 6 into 5 by 6 minus 2 into 1 by 9 minus 2 into 1 by 3 5 by 6, right? Next one, minus 2 into 5 by 6 whole square. This value finally 25 by 6. 25 by 6. This is the problem. This is quadratic programming problem by using what method? Wolfe method. By using Wolfe method. Any doubts? Once you practice the problem, you will get the solution. And I'm giving one problem for you to solve this one. Anyway, I will solve and post it to you. Definitely. Tomorrow I will post it. If any doubts, you can ask. If you provide a use Wolfe method to solve maximize z equal to 2x1 plus x2 minus x1 square subject to the constraints 2x1 plus 3x2 less than or equal to 6, 2x1 plus x2 less than or equal to 4. Two constraints are here. Okay, same procedure. Two constraints are here. Solve this. Try to solve this problem. Okay, I will solve this problem and post it to you. Any doubts?